Hello everyone, my name is Lama. I am a PhD research fellow at Turbine Testing Lab, Department of Mechanical Engineering, Kathmandu University. In this current research in Hydropower technology, CRHTX, I will be presenting on the method of erosion prediction hill diagram to investigate the performance of transit turbine operated in sediment-laden water to predict the erosion affecting regions in these affecting conditions. My outline for presentation. I will be talking about the transit turbine, its terminologies and working, the theory behind the sediment erosion and its effect in transit turbine, hill diagram, reference case, and I will be conducting numerical analysis for the data of Jhimruk hydropower plant, and then result for the same will be obtained, and finally I will be talking about equal to. Now let me talk about the terminologies and working of transit turbine. Since we know that transit turbine is a reaction of type of turbine in which the water enters the turbine radially and exits axially. And there are five major components of transit turbine, that are the spiral casing, stay vane, guide vane, runner, and draft tube. When water from the penstock enters to the spiral casing, then it passes through the stay vane and then guide vane and finally to the runner and draft tube. When water enters from guide vane to the runner, then the rotation of the turbine takes place, and here the conversion of hydraulic energy into the mechanical energy takes place. And when this turbine shaft is coupled to the generators, then we can get the electrical energy here. Sediment erosion is the dynamic action of sediment flowing along with water impacting against the solid surface. While talking about the sediment erosion, there are abrasive and erosive erosion, and which are one of the major problems for hydropower plants operating in sediment water. So there are so many factors which are responsible for the sediment erosions. That are the sediment particles. In the sediment particles, there might be shape, size, hardness, and concentration, hydraulic design and operating conditions. While talking about the operating conditions, there might be the impingement angle, the velocity of the fluid, temperature, etc. And third one, the turbine material. Harder the turbine material, the lesser will be the erosion, and similarly the chemistry and surface morphology of the turbine material also matters for sediment erosion. Now let me talk about the design philosophy of transit turbine, and this is the velocity distribution in transit turbine. When the water from the spiral casing enters to the stay vane, the velocity will be around 10 to 15 meters per second, and when it enters towards the stay vane, it accelerates and the velocity will be increased. At the outlet of guide vane, the 50% of hydraulic energy is converted into the kinetic energy or velocity energy. When water enters from guide vane to the runner, it deaccelerates and again it starts to accelerate while it flows through the runner blade. And at the outlet of runner blade, the velocity will be around 40 meters per second. Since the velocity at runner outlet and guide vane outlet are higher, and these are identified as the key factors or key reasons so that the erosion at the runner outlet and guide vanes are happening. Here the high relative velocity, due to the high relative velocity, the erosion at runner outlet is happening. Here, due to the highest absolute velocity and acceleration, the erosion at guide vane is occurring. Now let me talk about the hill diagram. Hill diagram is also termed as isoefficiency curve. From this hill diagram, we can identify the exact behavior and performance of the turbine under different operating conditions. In a hill diagram, for a given efficiency, there will be two values of speed values. There will be two values of speed and two values of discharge for a particular gate opening. However, for maximum efficiency, there will be only one value of speed and discharge. The generation of hill chart for transit turbine involves the part of dimensionless speed factor NED at abscissa and dimensionless discharge factor QED at ordinate along with defined guide vane openings. Hill chart also tells us about the the exact speed of turbine at which the best efficiency is obtained for a specific guide vane opening. For a specific guide vane opening, we can find out the best efficiency. Also, hill chart also tell us about the highest efficiency, and the values associated that efficiency, so that at which conditions the peak efficiency would occur. We can identify these things from here. For conducting the research, the data of Jhimruk hydropower plant is taken as the reference case. The Jhimruk hydropower plant having 4.1 megawatt of each unit with net heat of 201.5 meter and discharge 2.35 meter cube per second is considered as a reference case. And this is the experimental data from Jhimruk hydropower plant, where the relative hydraulic efficiency was observed during 1st September 2003 to 11th November 2003. During these periods, the efficiency at all operating conditions were reduced drastically due to the sediment erosion effects. These are the eroded turbine components of Jhimruk hydropower plant. Here, this is the outlet of turbine components, the erosion at the run inlet, and this is the erosion edge. For conducting the numerical study, the turbine of Jhimruk hydropower plant with 24 number of guide vanes and 17 number of runner blades were used. In order to minimize the computational time period, passage modeling technique with the 3 runner vane and 4 guide vane are considered in all the simulations. Mass flow rate at inlet and static pressure at outlet are chosen as boundary conditions, and Tabakov erosion model was used for all the simulation, and GCI technique was used for mesh independent study. These are the sediment properties used for conducting this. Here I will be talking about the development of leakage flow. In this section, the development of leakage flow is observed at various operating conditions. In order to investigate the leakage flow developed from clearance gap of guide vane, 6 different planes with a rectangular cross section were created at equal geometrical distances. At all cases, the influence of leakage flow was observed from nearly mid-span of guide vane. The intensity of leakage vortex as presented by velocity swirling strength is higher for part load and full load than that of best efficiency point. The highest vortex in part load and full load operating conditions may be due to the higher pressure difference in guide vane at those conditions. Thus, more leakage flow occurs. Therefore, the leakage vortex will have minimum effect at the design conditions compared to the part load and full load. Now, let me talk about the vortex travel and sediment erosion. Here, the combined effect of vortex travel from clearance gap of guide vane and sediment erosion is studied. This figure shows the trajectories of leakage vortex traveling from clearance gap of guide vane to the runner. Apart from primary tip leakage vortex, intermediate vortices, also termed as secondary vortices, are observed in part load and full load conditions. These are caused due to the improper stagnation. In this section, let me talk about the comparison of efficiency and erosion hill diagram. In order to generate a hill diagram, numerical model was investigated at 11 guide vane openings, that is 1 as best efficiency point, 5 towards part load and 5 towards full load. Similarly, for runner rotation, the speed was varied from 750 rpm to 1200 rpm with 50 rpm increment changes in each guide vane opening. Thus, in total, there are 110 different operating points were investigated to generate the efficiency and erosion hill diagram. The tolerance for head variation was maintained less than 1% at any operating condition, which was the most challenging task. While talking about the efficiency hill diagram, the efficiency was normalized corresponding to the best efficiency point. Here, the best efficiency point is shifted towards the part load condition. However, at speed variation was only 12% at that time. If the efficiency can be compromised slightly away from the best efficiency point, the speed variation up to nearly 19% can be achieved within the range of guide vane opening. This means we can say that the variable speed operation of turbine can be more powerful to recover the hydraulic losses that occurs during the change in operating condition. Now, let me talk about the erosion prediction hill diagram. The erosion prediction hill diagram is plotted against efficiency hill diagram. In this case, erosion resistivity, which represents the dimensionless value of erosion rate with reference to erosion at BAP is used. Thus, lowest value represents the lowest erosion wear. In this figure, the erosion resistivity narrows down towards the part load than that for best efficiency point, which suggests that analytical assumptions of flow behavior in part load is different when all the conditions are considered. Here, envelope below highly part load represents the least sediment affecting region, but the deviation in erosion rate is less than 8% from -5 degrees to the best efficiency point. This gives clear idea that the operating points should be shifted more from best efficiency point towards the part load to minimize the erosion effects. This also coincides with the fact that efficiency is also shifted more towards part flow with the least deviation from best efficiency point. Now, this is the future direction for my research. Once we have a problem, we must have a solution. We must have to find a solution. For that, so many techniques have been implemented in order to prevent the sedimentation to the turbine components. For that, designing a turbine is a key factor. For that, we have to design a turbine. We have to make the efficiency hill chart for the same. We have to make a sediment erosion hill diagram for the same turbine, and we should analyze both the turbine, and ultimately we have to implement the optimization, multi-objective optimization, thereby having the maximization of efficiency and minimization of sediment erosion. Lastly, by saying these things, I would like to conclude my presentation. From the research, we can say that the intensity of leakage vortex is seen higher in part load in full load conditions. Due to the secondary vortices and intermediate vortices, the erosion on the round outlet was seen more in off-design conditions. In the efficiency hill diagram, the efficiency was shifted towards the part load conditions, and in order to get the best efficiency point, and the run-out rotational speed can be varied up to 12%. The erosion hill diagram can predict the lowest erosion towards the part load operating conditions that we have seen in the hill diagram. Lastly, from the extreme part load conditions to the best efficiency point, the deviation in erosion was obtained only 8%, which means we can say that the turbine can be operated from best efficiency point towards the part load conditions to achieve the least erosion and highest efficiency. Thank you everyone for your kind attention. If you need any further information or if you have any question, please write to me in this email address. Thank you once again. Thank you very much.